Okay, welcome back. We're almost done. This is the final portion of our discussion in session 18 on plane stresses. And in this last portion, in this last part, what we're going to do is discuss how we go about calculating in-plane max shear stresses. Okay, and we're now fairly familiar with them. Okay? We're looking at a situation where we're rotating an element, okay, which I don't have the original orientation here on this kind of overview slide, but we're rotating, all right, to get to some sigma x prime, sigma y prime, and really what we care about, and there's a shear stress, right, and we're caring about getting these shear stresses, or this shear stress, to be a max, right, and we're going to have some sigma s and some, or sigma s1, sigma s2 associated with it. So now we can go to our equation that we derived for stress transformation for the shear stress. And like we did for max and min in-plane principal stresses, we can say we want this to be a maximum, which means we're going to set the derivative equal to 0. Okay, so we take the derivative of this expression, set it equal to 0, and then once again, we look at a condition where we can have an angle theta associated with this derivative of the shear stress with respect to theta being equal to 0. And that's what you see, that's what we see here. Okay. And once again, to help us be able to plug thetas back into the original stress transformation equation for the shear stresses, we can draw some triangles. Okay, so we say, oh, now if the numerator is this minus sigma x minus sigma y divided by 2, okay, we could say that's our opposite. We can say that we have a tau xy being our adjacent, and our angle is 2 theta s1, okay, right in here. And we can also flip around and go here where we have the inverse, right? So now we're going to say we have positive sigma x minus sigma y divided by 2, and we have a minus tau over xy. It's the same overall quantity, okay? Just flipping the sign from the top to the bottom. And we can say that we have 2 theta s2 as described here, okay? And if we want the hypotenuse of this expression, or sorry, of this side of the triangle, right, we can say, all right, well, it's the square root of this squared plus this squared, okay, and that's what we have here. And it turns out, okay, that this expression is pretty nifty and pretty useful. It's the hypotenuse here, and when you plug it back into the original equation, it also ends up being the max shear stress that you have here. We can also discuss having an average, okay, normal stress. And we kind of showed that graphically previously, okay, but this average that we have here is going to be giving us what the normal stresses are for the orientation associated with maximum in-plane shear stress. And in many cases, this average is not 0, right? But in the case of pure shear, which we discussed previously, right, there is this potential to have 0 normal stress when you have maximum shear stress. And that came out actually in question 18.3 and in the previous portion. And here what you could see is that, look, if sigma x and sigma y are additive inverses of each other, then that's what you're going to get. Okay, that this is you can have a situation of pure shear where you have a maximum shear stress, but you have no normal stress. So here are the expressions for n again, just in a little bit nicer, tidier form, okay, for you to use, and of course put on your formula sheet or your note sheet for the next exam. And then as practice, you and I, or we, can do the same problem that we just described, okay, where we have combined loading with a P pulling this negative tension and torque being applied, okay, Tap, right? That's twisting the shaft as shown. So it's an opportunity to figure out what the maximum in-plane shear stress might be under this condition. And yes, fortunately, you say, oh, this is the shortest one. Yes, this is the shortest portion. Yes, we've covered quite a bit, though, in this session. Okay, so we've discussed what are in-plane principal stresses, right? And kind of the simple answer is you've got a maximum and a minimum normal stress, and you've got zero shear. What are in-plane maximum shear stresses? State where you have maximum shear stress, and you have some average normal stress associated with it. And it's possible that that average could be equal to zero. We figured out how you can calculate the in-plane principal stresses using a fairly straightforward equation. And similarly, we found how to calculate the in-plane max shear stresses. Thank you for watching. And I hope that this session with its 4 portions has been informational and somewhat helpful. Till the next time.